Before we look at the quantitative values, let's think about this in a qualitative way. Imagine you're at the beach. When you go out on the beach in the morning, what do you notice about the temperature of the sand and the temperature of the water? The sand might feel cool on your feet, and the water is a comfortable temperature. Now let's consider the afternoon. When you go back out onto the beach in the afternoon, what do you notice about the temperature of the sand? It's probably burning your feet, and you're going to notice that the temperature has changed dramatically. But when you go in the water, you notice that there's very little change in the temperature of the water. And this has to do with the specific heat capacity of the water versus the specific heat capacity of the sand. Let's look at the specific values for water and sand. For water, we have a specific heat capacity of 4.184 joules per gram degree Celsius. We have a higher specific heat, and that tells us that the substance is going to be harder to warm up. When I look at sand, which has a specific heat capacity of 0.830 joules per gram degree Celsius, we see it has a lower specific heat capacity, and it's easier to warm up. So we've seen the sun shining on the sand heats the sand up fairly quickly. The temperature changes in water are minimal, so we have a smaller delta T, and delta just represents the change, so a smaller change in temperature. And the sand, which has the smaller specific heat capacity, has a larger delta T, or a larger change in temperature from morning to afternoon. Let's look at the equation that relates heat to the specific heat capacity. We have Q equals M times CS times delta T. Q is the heat, and so this is energy, and so it has some unit of energy associated with it, which could be joules, kilojoules, calories with a little c, or calorie with a big C. We then have mass, which is typically in units of grams. Our CS, which is our specific heat capacity. And it has units of joules per gram degree Celsius or calories per gram degree Celsius. And then we have our delta T, which is the change in temperature. And we represent this as the final temperature minus the initial temperature. Anytime you see the delta in front of a variable, it's always final minus initial. Since heat can be in different units and the specific heat capacity can be in different units, we always need to make sure there's a match among the units. So if we're given joules per gram degree Celsius, then we want our heat in units of joules, and we want our mass in units of grams. For temperature, the equation has degrees Celsius, but we can actually use either degrees Celsius or Kelvin because we are looking at a change in temperature. Remember that when we convert from Celsius to Kelvin, it's just a difference of 273. It's an addition or subtraction, not a multiplication. The delta T in degrees Celsius will be the same as the delta T in Kelvin. 100 joules of energy is applied to a 25-gram sample of water at an initial temperature of 28 degrees Celsius. What is its final temperature? We're given the specific heat capacity of water as 4.184 joules per gram degree Celsius. So now we can start filling in the values that are given in the problem. We know we're given 100 joules, 25 grams, and the initial temperature of 28 degrees Celsius. So we plug in 100 joules, 25 grams, the specific heat capacity of water, 4.184 joules per gram degree Celsius, and then we have TF minus 28 degrees Celsius. Notice that we changed the delta T to TF minus TI because we know one of the temperatures but not both. Now we can multiply the 25 times 4.184 and get 104.6 times our TF minus 28. I'm then going to divide both sides by 104.6 and we get 0.956 equal to TF minus 28. We add 28 to both sides and get 28.956. Rounding for sig figs, we get 29 degrees Celsius equals the final temperature. Now let's look at a similar problem, but dealing with a sample of sand. 100 joules of energy is applied to a 25-gram sample of sand at an initial temperature of 28 degrees Celsius. What is its final temperature? Notice that we have 100 joules, 25 grams, and an initial temperature of 28 degrees Celsius. All of these three pieces of information are the same as they were in the previous problem for water. What's different is the specific heat capacity of sand versus that of water. We're going to plug in our values. 100 joules equals 25 grams times 0.830 joules per gram degree Celsius times TF minus 28. Again, multiplying 25 times 0.830, and we get 20.75 times TF minus 28. Now we can divide both sides by 20.75 and get 4.82 equals TF minus 28. Add 28 to both sides, and we get 32.82 equals TF. Rounding for significant figures, we get TF is equal to 33 degrees Celsius. Same amount of energy, same mass, different final temperature. Let's compare the values we got for the two problems. Both of them had the same value of Q, so the same amount of energy. Both samples had the same mass. The initial temperature for both was the same, but we see that the final temperature for the water is 29 degrees Celsius. The final temperature for the sand was 33 degrees Celsius. And this is a result of having different specific heat capacities. For the water, which had a higher specific heat capacity, we saw a smaller delta T, or a smaller change in temperature. For sand, we saw a lower specific heat capacity, therefore we had a larger delta T, or a larger change in temperature.